Alright, so in this video I'm going to be explaining another important article about domain adaptation, which is discriminative feature alignment, improving transferability of unsupervised domain adaptation by Gaussian guided latent alignment. So this article in 2020. In this paper, we focus on the unsupervised domain adaptation problem where an approximate inference model is to be learned from a labeled data domain and expected to generalize well to an unlabeled data domain. The success of unsupervised domain adaptation largely relies on the cross-domain feature alignment. Previous work has attempted to directly align latent features by the classifier-induced discrepancies. Nevertheless, a common feature space cannot always be learned via this direct feature alignment, especially when a large domain gap exists. To solve this problem, we introduce a Gaussian guided latent alignment to align the latent feature distributions of the two domains under the guidance of the prior distribution. In such an indirect way, the distributions over the samples from the two domains will be constructed on a common feature space, the space of the prior, which promotes better feature alignment. To effectively align the target latent distribution with this prior distribution, we also propose a novel unpaired L1 distance by taking advantage of the formulation of the encoder-decoder. You see, the existing unsupervised domain adaptation methods try to align the feature distribution of the two domains by the classifier-induced discrepancy. So this is the classifier-induced discrepancy. We have this target feature distribution and this source and try to match them. However, it might be difficult for them to construct the two feature distributions in a single space or align arbitrarily complex feature distributions in that space. Our method attempts to indirectly align the features of the two distributions under the guidance of the Gaussian prior distribution. Our method can encourage the feature of the two domains to be constructed in a common feature space. We call it the space of Gaussian prior, where the target samples can maximally take advantage of the discriminative source features for their own classifier. So we have a middle space, the Gaussian space. We propose a novel model for unsupervised domain adaptation which utilizes an indirect latent alignment process to construct a common feature space under the guidance of a Gaussian prior. We introduce a new method to align two distributions which, instead of minimizing the discriminator error using a GAN, minimizes a direct L1 distance between the decoded samples. So this is aligning two distributions by taking advantage of the formulation of encoder-decoder. It contains an encoding function G and a decoding function D. The mapping function D of G can be regarded as a weighted tied autoencoder that can put less representative features into a nonlinear regime of G's. So we have adversarial domain adaptation and non-adversarial domain adaptation, like maximum mean discrepancy. Sample n-labeled images from the source space to form the source domain, as well as m unlabeled images from the target space to form the target domain. The objective is to obtain a feature extractor that generates a target distribution in the feature space that can maximize the performance of classifying x sub t without accessing its label. Knowledge transfer via encoder-decoder. The proposed work is under the assumption that every neural network-based UDA framework should consist of a feature extractor G and an image classifier F. The goal is not only to align the latent distributions of the two domains, but also to make G learn the representation from the target samples under the guidance of discriminative source representation. So the decoder D is specifically used for proposed distribution alignment loss to align the target latent distribution with the prior distribution. G is also an encoder that learns the hidden representation for both this image classifier and this decoder. As G continuously shares its learning parameters with D during the training, our model can also be viewed as a weight-tied autoencoder. The proposed distribution alignment loss, which is different from the reconstruction loss used in the existing work on autoencoder, is an L1 distance between the reconstructed target samples and the decoded samples from the prior in the feature space. And view knowledge transfer via distribution alignment. We are interested in learning the correspondence between samples from target latent space and the samples from the source input space. Where the encoder G shares its learning parameter theta with the decoder D. The mutual information between the source input space and the target latent space can be expressed as I. So H here is the entropy. H is an unknown constant since the source input space x sub s is from a fixed distribution that will not be affected by theta. So what is important is this one. Normally the reconstructed target sample x hat is not exactly the same as the corresponding source sample x sub s. However, in probabilistic terms, the parameters of a distribution may produce x hat with high probability as they share the same object feature. Therefore, the lower bound of mutual information can be maximized by minimizing this. L1 is just the L1 distance. However, this objective cannot be achieved because of the lack of correspondence between the reconstructed samples from the target domain and the input samples from the source domain. To tackle this problem, so the heart of this paper is this section. We define a prior distribution Q and construct the discriminative source features on the space of prior Z. If there exists the KL divergence between them is equal to 0 and ZS, then we can rewrite it like this. Now we can define a distribution Q for the following inequality. The left-hand side of equation 6, which is this side, is the lower bound of the mutual information between the source input space and the target latent space. We thus have a new lower bound for the mutual information. Considering the parametric distribution Q hat Q, the lower bound here can be approximated by just maximizing the expectation of log of Q, because we have the lower bound. Therefore, the mutual information I can be maximized when there exists some theta such that Q is equal to P. Now we combine it with 5 and 8. Combining 5 and 8, we have the lower bound of the mutual information. Just maximize this one. Now we consider the distribution alignment error. So what is important is this distribution alignment error. We thus have the following minimization that is equivalent to maximization of the lower bound. So we can conclude that the lower bound of mutual information between the source input X sub S and the target latent space Z sub T can be maximized by minimizing the proposed distribution alignment error L1 on the premise that the source latent distribution is close enough to the prior. Now we talk about the decoder part, because the proposed regularization has two functionalities in our model: distribution alignment and discriminative feature extraction. The distribution alignment mechanism alone cannot guarantee the produced latent distribution is adequately discriminative for F to generalize well to the target domain. To further enforce G to focus on the cross-domain classification discriminative to generalize well to the target domain, to further enforce G to focus on the cross-domain classification discriminative characteristics of target samples, we let the weight matrices of G and D be symmetric. The choice of weight tying for the proposed encoder-decoder is motivated by the denoising autoencoder. This denoising autoencoder shows that tying the weight makes it more difficult for an encoder to stay in the linear regime of its nonlinearity. We denote a mapping layer G followed by a nonlinearity sigma sub I. Similarly, we define a mapping layer of D followed by the same nonlinearity sigma sub I. So without considering the pooling, unpooling, and batch normalization, our 2L layer autoencoder with tying weight is this one. The average unpooling utilized for decoder is the upsampling using the nearest neighbor interpolation. The max unpooling used for the decoder is this torch neural network max unpool 2D, which is implemented by PyTorch. So we are aligning the two distributions by this encoder-decoder formulation. And we use soft max cross entropy to handle classification task on the label source domain. But to encourage the latent feature distribution of the source domain to be close to the Gaussian prior, we apply the KL divergence penalty between P and Q to regularize G. And G seeks to generate the discriminative features of the source domain in the space of prior under the support of L. We investigated the most effective method for latent alignment in this ablation study. We conducted a case study on the adaptation scenario from MNIST to UPSP. To better illustrate this study, we first define some loss functions. We formulate the paired reconstruction loss of an autoencoder. So this is a reconstruction loss that you know in autoencoder. Now this is the overall architecture. The feature extractor G maps the input data to their latent feature vectors. Now what is our latent? Is just the Gaussian. The decoder D can be viewed as an inverted version of G, which maps a latent feature vector to Gaussian. Or Gaussian prior vector to an image that has the same dimension as input samples. So now that we have got the Gaussian with the generator, the decoder turns this into the image. So the same autoencoder that you are familiar with, but with the target and source you have shared weights, and also here we have shared weights. And so we are trying to mimicking the idea of autoencoder for domain adaptation. So regularizing G and F makes the discriminative feature space of the source domain be constructed on the space of the prior. Therefore, by encouraging P of Z to be defined in the same distribution space, tasks on the target domain can maximally take advantage of the knowledge learned from the source labels. To achieve this, we propose a simple yet effective method to align the target latent distribution with the prior distribution, namely distribution loss, alignment loss. This distribution alignment loss is applied to regularize both G and D. We utilize the absolute difference between the two data distributions produced by D and formulate the proposed distribution alignment loss. And you see this one is just the L1 norm. So the latent feature vector Z sub T is fed into F to produce predictions for the target input samples. To control the contribution of the target predictions in the generalization of an image classifier, we employ a low-density separation technique, entropy minimization, to measure the class overlap of the target samples. So we have the full objective, which is we have a cross entropy loss, we have KL divergence loss, we have distribution alignment loss, and entropy loss. So maximum classifier discrepancy achieves the state-of-the-art on logit and traffic sign classification. It has one feature extracted G and two image classifiers f sub 1 and f sub 2. It regards the disagreement between f sub 1 and f sub 2 as its classifier-induced discrepancy. It uses a three-step adversarial training strategy to avoid the input target samples that are outside the support of the source domain. First, minimizing the softmax cross entropy. Second, minimizing the difference between classification loss and the L1 loss between the outputs of the two image classifiers on the target samples. And third, minimizing the adversarial loss.